In this and previous lectures, we have been discussing the concept of chemical potential. We have shown that for a gas J, either pure with pressure P sub J or present as one component in a mixture with partial pressure P sub J, we write the chemical potential of gas J equals to the standard chemical potential of J plus RT times the natural log of P sub J divided by P standard. For a solvent A obeying Raoult's law, the chemical potential of A in solution is equal to the standard chemical potential of A plus RT times the natural log of XAL. For a solute B obeying Henry's law, the chemical potential of B in solution is equal to the standard chemical potential for ideal dilute B plus RT times the natural log of XBL. Alternatively, using Henry's law with molarities, the chemical potential of a solute B in solution is equal to the standard chemical potential of B plus RT times the natural log of XBL. If we examine all these expressions of the chemical potential, we can obviously see a pattern and write in general that the chemical potential of a component J in a mixture is expressed as some standard chemical potential, which we write in general as mu J standard, plus RT times the natural log of a term, which we will call from now on the activity of substance J. The activity of a substance will be defined differently depending on the phase and the concentration of the substance. For ideal gases, the activity is simply the ratio of the partial pressure over the standard pressure. For a solvent obeying Raoult's law, the activity is the mole fraction of the solvent. For a solute obeying Henry's law, the activity can be the mole fraction of solute or the solute molarity. We can even extend this generic representation of chemical potential in terms of activity for pure liquid and pure solids by assigning them an activity equal to 1. Indeed, the chemical potential of a pure liquid or a pure solid must be equal to the standard chemical potential. If their activity is equal to 1, the natural log of their activity is equal to 0 and their chemical potential is equal to their standard chemical potential. On the preceding slide, we introduced the concept of activity for solvent and solutes when they obeyed Raoult's and Henry's law, respectively. However, we also indicated earlier in this lecture that when a solution is not very dilute, then the solvent does not follow Raoult's law and the solute does not follow Henry's law. So, how can we define the activities and express the chemical potentials for solvent and solute under these conditions? Before introducing Raoult's law and ideal solutions in lecture 3-4, we had actually derived a general expression for the chemical potential of any component of a solution and written for the solvent A, the chemical potential of A in solution equal to the chemical potential of pure A plus RT times the natural logarithm of PA over PA star. The same form of expression was also derived for the solute. Examination of this expression for mu A indicates that the activity for A is the ratio of the partial pressure of A over the vapor pressure of pure A at the same temperature. Now, if Raoult's law does not apply, we cannot write PA over PA star equal to XAL. But we can introduce a quantity called gamma A to account for the departure from Raoult's law behavior and write PA over PA star equal to gamma A times XAL. Gamma A is the activity coefficient for A. Its value must approach 1 when the mole fraction of A approaches 1, since we know that as a solvent becomes almost pure, its behavior starts to follow Raoult's law. Similarly, we can define an activity coefficient for the solute B called gamma B, such that the activity of B is equal to gamma B times the molarity of B divided by the standard molarity. Again, we expect the activity coefficient for B to approach 1 when B enters the ideal dilute solution behavior, starts to follow Henry's law. In both cases, activity coefficients measure the departure from ideal behavior, ideal solution behavior for the solvent, and ideal dilute solution behavior for the solute. Actually, activity coefficients provide more information than just a measure of departure from ideal solution or ideal dilute solution behavior. Activity coefficients provide information about the nature of the solvent-solute intermolecular interactions. First, recall that we define gamma B as Pb over XBL Pb star. Pb is the actual vapor pressure of component B above the solution, while XBL Pb star is the partial vapor pressure that the solute B would exhibit if it followed Raoult's law. On the graph of vapor pressure of B versus mole fraction of B in solution, we have represented the magnitude of Pb with the blue arrow and the magnitude of XBL Pb star with the red arrow. For the vapor pressure diagram chosen here, the blue arrow is greater than the red arrow, and we say that we have a positive deviation from Raoult's law. This implies that gamma B is greater than 1. The fact that Pb is greater than the ideal value, XBL Pb star, implies that B is present at greater concentration in the vapor phase than it would be if the solution was ideal. If you remember that in ideal solutions, all intermolecular interactions, AA, BB, and AB are the same, then you must conclude that a greater concentration of solute in the vapor phase is indicative of non-favorable interactions between B and A in solution. In other words, if solvent and solute do not like each other, they would rather be in the vapor phase, where their interactions are minimized, than in solution, where they cannot avoid interacting. Obviously, if a solvent does not like a solute, then the solute does not like the solvent. And what we have just said for the solute applies also to the solvent. If gamma B is greater than 1, then gamma A is also greater than 1. Conversely, if Pb is less than XBL Pb star, then Pa is also less than XAL Pa star, and both gamma A and gamma B will be less than 1. This situation corresponds to negative deviations from Raoult's law and leads to a vapor pressure diagram where both Pa and Pb curves are below the Raoult's law for all composition. This situation is associated with a pair of solvent and solute molecules that like each other and would rather be in solution where they can interact favorably than in the vapor phase where they do not interact very much.